Hello, I welcome you all. The problem reads draw the shear and the moment diagrams for the beam. This problem is coming from the Engineering Mechanics and Statics textbook, 13th edition by R.C. Hibbeler. So we have a beam loaded with two concentrated loads, and it's a simply supported beam. So let's draw the free body diagram. At A, I expect AY and AX like so, and at B, we expect a BY. Right. Let's apply the equations of equilibrium. So summation of moments about point A equal to 0, and clockwise being our reference. What do we have? We have minus moment 6 by 2, minus 12 by 4, then plus by 6 equal to 0. Okay. Therefore, my by is just going to be equal to, by will be equal to plus minus 6 by 2, then minus 12 by 4, then divided by 6. So we get a we get a plus 10. It's just a 10, right? 10 kilonewtons. Then we have summation of forces in the y for us to find the value of ay. So we'll have ay plus by minus 6 minus 12 is equal to 0. So this is our B. This is our B. Therefore, our AY is just going to be equal to 10 minus 6 minus 12. AY is equal to 8 kilonewtons. Then finally, we have summation of forces in the x direction equal to 0. What do we have? We have AX equal to 0. Let's label this. By is equal to 10 kilonewtons. Ay is equal to 8 kilonewtons. Ax is equal to 0 kilonewtons. Alright, so because we have a lot of intervals, if we were to use equations, we are better off just using two differential equations that relates the distributed load to the shear to the moment. So the rate of change of moment with respect to x is equal to the shear V, and therefore moment is equal to the area under the shear diagram. And the rate of change of shear with respect to x is equal to the distributed force Q, and therefore the shear force is equal to the loading under the distributed loading. The area under the distributed loading is equal to shear. So with these two differential equations, we are able to draw our shear force diagram. So let's do that quickly. There we go. Alright. So we have positive up, negative down, positive up, negative down. Okay. So let's start drawing. So at A, we expect at A, we have this value, the initial value of 8 kilonewtons. 8 kilonewtons. And then from A, let me call this as C, D. From A to C, Q there is equal to 0. Therefore, the slope of our shear diagram is also just going to be equal to 0. And hence, just a constant I mean just a straight line with zero slope. Okay, up to C. When we arrive at C, we have a point load which has magnitude of 6 and is negative. So the two are going to interact. So we have 8 minus 6 equal to 2. Okay, so that the shear at that point is going to reduce by 6 units, and then we are going to, its final destination will be 2 kilonewtons. All right, to be 2 kilonewtons. Okay, right. And then from C to D, as usual, Q is equal to 0, so you expect dV dx equal to 0, which is the slope of our shear diagram. So we just expect 0 slope up to D. Then when we reach D, the two are going to interact. We have a 2 positive, then a 12 which is a minus. Okay, therefore we have a minus 10. So the shear of 2 will reduce by 12. Okay, so when that happens, then we expect our shear diagram to reduce up to the value of minus 10. Let's say 10 is somewhere there. Okay, let's say this is our 10, minus 10. Okay, right. Then again, from D to B, Q is equal to 0. So we expect the slope again to be equal to what? 0 slope for shear. So we expect again just a 0 slope up to there. When it reaches where we have B, then there's going to be an interaction there. We have a minus 10 plus 10, which is equal to what? 0. A closure. We need to close and get our money. All right, get our money. Okay, closed the business. All right, so we have a positive shear there, we have a negative shear there. Great, so we are done with the first part. Let's plot the other part. Again, we are going to use the same differential equations, but we'll be using shear to relate it to the moment. From A to C, our shear is positive 8, and it is constant. Okay, therefore the slope of our moment also, dm dx, will be positive and constant. Okay, do we have any moment at A? No. Can support A resist any moment? No. So we need to be considerate of the boundary conditions when we are using this method. All right. Therefore, we know that at A, the moment will start from 0. It will be 0. And it will have a positive constant gradient. And what's its magnitude? This magnitude, we know that M is equal to the area under the shear diagram, which is just equal to 8 times the length of that rectangle 2, which gives us a 16. Great. So let's move from 0 to 16. Let's say 16 is somewhere there. I'll need to still move downwards a little bit so that I have some space. I'm seeing myself running out of space. Okay, let me just take this a little bit down, maybe up to somewhere there. Great. So let's redraw that 16. So from there, let's say we are moving up to there like that, something like that. All right, so we said that value is what? The magnitude is what? is 16 kilonewtons meter. All right, great. And then what happens from C to D? From C to D, our V is again positive and constant, positive value of 2. Therefore, our moment dm dx will also be positive and constant. And the magnitude of our moment is the area under the shear diagram, which is just equal to 2 times 2, which is equal to 4. You need to know where you're coming from. There is a value, an initial final value, which is 16. So the two will interact, all right? So they are both positive, so it's 16 plus 4, which gives us a 20. Okay, it has a positive gradient. All right, but the gradient for the next one will be lower because the gradient for the first one was 8, the second one will be 2. Okay, so we expect a linear, okay, increase. So from there, we expect a movement from there to, let's say, up to 20. Up to 20, not a very good one. Okay, let's say up to there, like so. So that value there, we said, is a 20 kilonewtons. This is a 20 kilonewton. This is a 20 kilonewton meters. All right. And then finally, from D to B, shear is negative and constant, and the slope dm dx is also going to be equal to negative and constant, and the magnitude is going to be equal to area under the shear diagram or the shear loading, which is just equal to a minus 10 times 2, which is equal to minus 20. So the 2, mind you, the final position where we ended, we have a positive value of 20 kilonewtons. So the 2 will interact. So we'll have 20 positive minus 20, which gives us a 0. Therefore, this part here, like we said, it will have a negative constant gradient. All right, so we'll have a movement from there to 0, like we said, up to okay, up to there, something like that. Okay, there we go. And this one is positive moment. So this is really about it. This is about it. We have the shear force diagram and the bending moment diagram. I hope the video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.